Hi, in this video we will go through some worked examples, computing the SVD and using the SVD in a number of application types. Let's begin with an example, finding the SVD of a general matrix. Can we find the singular value decomposition of this 2x3 matrix A? I recommend you pause your video, try to solve this problem, and then resume to follow along with my solution. The first step in finding the singular value decomposition is always to find the eigenvalues of A transpose A. This is kind of the heart of the singular value decomposition. A transpose A will always be a symmetric matrix. It will always have a well-defined eigenvalue decomposition with orthogonal basis vectors, and we can use that as the core of the singular value decomposition. So we start with our matrix A and evaluate A transpose times A. So if A is 1, negative 3, 0, 3, negative 1, 0. A transpose, of course, takes each row, makes it a column. Each row makes it the column. And then we do the multiplication. 1 plus 9 is 10. Negative 3 minus 3 is negative 6. And 0 plus 0 is 0. Negative 3 minus 3 is negative 6. 9 plus 1 is 10, 0 plus 0 is 0, and the last row is 0, 0, 0, 0, 0, 0, so a row of all zeros. A was a 2x3 matrix. A transpose A will be 3x2 times a 2x3 should give us a 3x3 matrix, which is exactly what we see here. Again, we note this is a symmetric matrix. Once we've found the matrix itself, we are ready to go ahead and find the eigenvalues of this matrix. We find the determinant lambda I minus A transpose A. This is lambda minus 10. Negative negative 6 is 6, 0. Negative of negative 6 is 6. Lambda minus 10, 0. And 0, 0, lambda. We can evaluate this determinant with cofactor expansion along either the last row or the last column. In terms of the signs, we have plus, minus, plus. So we're starting with a plus, plus, minus, plus, which means we have a plus sign for the expansion. Signs don't actually really matter too much here, but let's be careful with it anyway. We have a lambda multiplied by the determinant after crossing out this. This is the determinant of the 2x2 with lambda minus 10 is on the diagonals and 6 is on the off diagonals. This, of course, is lambda minus 10 squared minus 6 squared. Expanding out this, lambda minus 10 squared is lambda squared minus 20 lambda plus 100. 6 squared is 36. 100 minus 36 is 64. So we're looking for a pair of numbers that add to give us negative 20, the negative lambda term here, and that multiply to give us 64. Negative 16 and negative 4 satisfy this. So we can factor this out into lambda, lambda minus 16, lambda minus 4. Setting this determinant equals to 0, the characteristic polynomial equals 0, gives us 3 eigenvalues, 16, 4, and 0. Now, these are the eigenvalues of A transpose A. The non-zero eigenvalues are related to the singular values of the matrix A through the relationship sigma I squared equals lambda I, or sigma is the square root of lambda. So the non-zeros, 16 and 4, give us singular values of 2 and 4. This is already enough to construct the middle matrix of the SVD. Remember, the SVD, we're trying to find U sigma V transpose. If A is a M by N, U will be square M by M, V will be square N by N, and sigma will always be the same size as A. A was 2 by 3. Our sigma is then 2 by 3 with the non-zero singular values put as the diagonal elements in decreasing order. So 4 and 2. All right. Those are the singular values. The next step is to find singular vectors. We begin by continuing looking at A transpose A, the matrix shown here, with eigenvalues of 16, 4, and 0. And we do we find the eigenvectors associated with each of these. When lambda equals 16, be careful here, we use the eigenvalues of this matrix, not the singular values, which were the square roots. When lambda equals 16, lambda I minus A transpose A becomes 6, 6, 0, 6, 6, 0, and 0, 0, 6, which we have a duplicate row that will become all zeros, divide everything through to scale so that we have our pivots of 1, and a free variable in the middle. We get our special solution to the homogeneous system described by this coefficient matrix by setting our free variable equals to 1 and reading off the pivot entries from the corresponding column, negating them, negative 1, 1, 0. This is a special solution. This does not have a norm of 1. In the singular value decomposition, we need to find orthonormal eigenvectors, and so we scale this by the length of this, the square root of 2, in order to get a orthonormal eigenvector. We then carry on. Lambda equals 4. Lambda I minus A transpose A gives us 4 minus 10 is negative 6. 6, 0, 6, negative 6, 0, 0, 0, 4. Again, we have a row that's a scalar multiple of the other. That's going to disappear. And when we scale each row to give us our pivots of 1, we get 1, negative 1, and 0, 0, 1. Same idea. We have a free variable in the middle. We set that equal to 1. We read the pivot entries off of the corresponding column, negating them, gives us 1, 1, 0. Again, this is not normalized. Normalizing it gives us 1 over root 2, 1 over root 2, and 0. Right. These were the eigenvectors associated with non-zero eigenvalues. We then take the 0 eigenvalue, which is the same as looking at the null space of this matrix. Sorry, there should be negatives in here. Doesn't really matter, but there should be a negative 10 here and a negative 10 here because we're doing 0 minus those. Here, what we have is 2 linearly independent rows and a row of all zeros. So this is going to give us a final form of 1, 0, 0, 0. Actually, there's a step here that isn't really followed through. What would we do here? We would put a 10 and a 6 and subtract off 6/10 of this would give us a 0, and 10 minus 36/10 would give us some value here, a single value, which we can scale to give us a 1. We then eliminate upwards and scale the row. We get 1, 0, 0, 0, 1, 0, 0, 0, 0. 2 pivots, a single free variable. We set that free variable equals to 1. Pivot values are 0. This gives us our last vector, null space vector for A transpose A, and this is already normal because it's 0, 0, 1, so its length is 1. All right, now that we have our eigenvectors, these are the singular vectors v. Right? We have eigenvalue 16 corresponding to a singular value of 4 and an eigenvector. Remember, we had set sigma to be 4, 2, 0. We set them in decreasing order. The first column of V is this eigenvalue. For our second eigenvalue of 4, singular value of 2, we had this orthonormal vector. It becomes the second column. For our third eigenvector, this doesn't have a singular value associated with it. The singular values are positive, but we have a 0 eigenvalue corresponding to this. Sorry, there's not an extra row here. The last eigenvalue of 0 corresponding to the null space becomes the last column of V. V has to be square. We have to have this last column, 3 by 3. All right, so now we have sigma, we have V. Remember, we're aiming for A equals U sigma V transpose. The next thing we're going to be trying to find is U. How can we find that? Well, we can rearrange the A equals U sigma V transpose to be A V equals U sigma. We already have V, so we can compute this AV. We have sigma, which is diagonal. This will give us an easy way to find U. Compute A times V. A, 1, negative 3, 0, 3, negative 1, 0. V, as we constructed this, just go through and do the multiplication. Negative 1 over root 2 minus 3 over root 2 is negative 4 over root 2. 1 over root 2 minus 3 over root 2 is negative 2 over root 2. And 0, 0 plus 0 gives us a 0. Negative 3 over root 2 minus 1 over root 2, negative 4 over root 2. 3 over root 2 minus 1 over root 2 is 2 over root 2. Right? This is what A times V is. We have U times this singular matrix here needs to be equal to, U times this matrix sigma needs to equal this. Multiplying this by U is going to scale the columns, and so we can just look at this and say this multiplied, divided through by 4 gives us a column here. We just take this and we divide it by 4. To get the second column of U, we take the next column here. We see that there's a 2. We divide this by 2 to give us our second column of U. And the last column of zeros comes from this piece here. This gives us our final result, our U, sigma, and V, such that A equals U sigma V transpose. Okay, now let's move on to a problem finding a low-rank approximation to a matrix using the singular value decomposition. Can we find the best, or best is defined in a least squares sense, rank 2 approximation to the following matrix with the SVD given? Our matrix is here. Our singular value decomposition is here. This is a bit of a messy singular value decomposition. Not messy as far as arbitrary matrices goes, but not something that would be particularly fun to work through by hand. So we have it given here, so we can focus on using the singular value decomposition rather than finding it. Okay, once again, I recommend that you pause, see how far you can get on your own, and then continue to follow along with the worked solution. All right, the key to low rank approximations is to zero out all of the singular values beyond the ones that we are looking for a rank. So in this case, apologies, we are looking for a rank 2 matrix. We want rank 2. That means that we only keep 2 of the singular values. We can use exactly the same U, exactly the same V transpose, but we put in the middle a sigma 2, which only has 1, 2 non-zero singular values, and the places that had singular values in our full singular value decomposition become zeros. We then carry through with the multiplication. Now, when we multiply out a matrix like this, we're going to see some interesting things. First of all, the effect of multiplying diagonal matrix to the left of a target matrix is to scale each row by the diagonal entries. Because 2 of them are zeros, that's going to make 2 of the rows become all zeros. Right? It's essentially going to eliminate these 2 rows. What we're going to be left with is a row with 10 times these half, negative, half, negative, half, half, and a row of 2 times half, 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 half. This, of course, is going to give us a matrix 5, negative 5, negative 5, 5, and 1, 1, 1, 1, with zeros and zeros. When we then carry on the second multiplication, we're going to multiply each row by each column. We see that the first column has 2 zeros. Actually, every column has 2 zeros at the bottom. That means that every row we walk along, we are going to be ignoring this row and ignoring this row, because it's always, or this column and this column, because they're always multiplied by zeros. So what are our entries going to be? 5 times a half plus a half is 3. Negative 5 times a half plus a half is negative 2. This third column is exactly to the second, so it's also a negative 2. The fourth column is exactly the same as the first, so it's also a 3. For the second row, we see that the first 2 entries are identical to the first 2 entries of the first row. The second 2 entries don't matter. That means the second row is going to be exactly the same. These are going to end up being identical. For the third row, we have half times 5 minus a half is positive 2. Negative 5 halves minus a half is negative 3. Again, the third column is the same as the second. The fourth column is the same as the first. So we have negative 3 and 2 again. And the first 2 entries of the fourth row are identical to the first 2 entries of the third row. The entries in last 2 entries don't matter, and so we get, again, 2 identical rows. This is our rank 2 approximation. We can tell fairly obviously that this is rank 2. We have 2 pairs of identical rows, and those rows are linearly independent. 2 linearly independent rows, rank of 2. Finally, we can compare our low rank approximation to our original matrix. This original matrix was rank 4. So we've reduced to a rank of 2. And what's the difference? Well, our original matrix was 3, negative 2 1/4, negative 1 1/4, 3. And the low rank approximation has these middle entries the same rather than slightly different. So we have slight errors, negative 1/4 and plus 1/4. Similarly, for the second row, our original matrix had those same 2 entries swapped, but they're identical in the low rank approximation, giving, again, similar errors. The same kind of thing happens in our last 2 rows. The last 2 rows have identical entries in the middle, close but not identical entries on the first and last entries. The low rank approximation makes those equal to their average, again with corresponding errors. A low rank approximation to a full rank matrix. Right. We can see, actually, if we just go back a little bit to our eigenvalue decomposition, our singular value decomposition, it's not surprising that that low rank approximation works quite well. Our first eigenvalue is our first singular value is much larger than the second, right? 5 times higher. The second is 4 times higher than the third. The third is 5 times higher than the fourth. So actually, this largest eigenvalue is 100, or singular value is 100 times more important than the last in determining the matrix. This first singular value is 20 times more important than the third one. Because these last smallest two singular values are significantly lower than the first, we get a good rank 2 approximation. You might ask, what do you think that the rank 1 approximation to this matrix looks like? And how close would it be? All right. Okay. Now let's go to a third example, one applying the idea of principal component analysis. We're going to use this to find best fit lines and planes to a set of data. Can we find the best fit line and the best fit plane through the origin given the eigenvalue decomposition of AA transpose? This is the correlation matrix for the data matrix A. A consists of, in this case, 6 columns of 3 values each. We can think of each one of these as an X, Y, Z, a set of points in a 3-dimensional space. We have 6 points in some 3-dimensional space, and we'd like to know what is the best line through those points, what is the best fit plane through those points, and so on. Given this decomposition of AA transpose, which is the heart of the principal component analysis, I recommend that you pause your video, try to do this on your own, and then resume to follow along. Okay. So we are given, in this case, this AA transpose and its decomposition. AA transpose has to be a symmetric matrix. Remember, this is really the first step in doing the singular value decomposition. We compute A transpose A or AA transpose to get singular values. AA transpose is a 3 by 3 matrix that describes how the various pieces of this components X, Y, Z for these 6 points vary with respect to one another. This is the how they correlate with themselves, always sort of a fairly always a positive value that describes how spread out the data is. The off-diagonal elements describes how well correlated are the values with each other, the x and y and so on. With this AA transpose, we have a eigenvalue decomposition of this with a U, a set of eigenvalues, which are the same as the squares of the singular values, and a U transpose. How do we use these ideas to get best fit planes and best fit lines? Well, the best fit line is simply the line described by the largest principal component or principal vector. What do we mean by that? We look at our eigenvalues, singular value, the squares of the singular values, and our largest one is 321. This corresponds to the singular vector, the eigenvector of AA transpose listed here. This is the vector that describes the best fit line. We can describe the best fit line simply by any scalar multiple of this singular vector. And this kind of makes sense if you look at how these data are related. There's a lot of variation in the x component. There's a lot of variation in the y component. The y component is close to twice as high as the negative, but opposite in sign. And what do we see? We see x is negative 0.46, y is plus 0.88, close to twice, but opposite sign of x. The z component has a much smaller range of variation. It doesn't, and the correlations are a little bit harder to work out because whereas because they scale differently from the two x's and the y's. All right. Okay, so we get a 0 here. This is our best fit line. Very straightforward. How do we get the best fit plane? The best fit plane is simply found by taking the two largest principal components. The largest principal vector was 321. The principal singular value squared was 321. The next one is 10, much smaller. And the last one was less than 1. We take the two singular vectors corresponding to these and describe a plane with these. How do we describe a plane given two vectors? We take all possible linear combinations of either of those vectors. The plane that is a best fit plane to these data is described by k times this first singular vector plus L times this second singular vector. Thinking about how this captures the variation, well, the first singular vector captured this relationship between x and y that's close to anti-correlated with a factor of 2. We saw that y is approximately equal to negative 2x, that we see something featured in here. And L and the z component is treated separately. So the second principal component just captures the z piece of this. All right? This is our best plane for the data. Okay. Now, moving on to a last example, how can we solve a problem using a pseudo-inverse given by the SVD? Can we find the general least squares solution to a system of equations given the singular value decomposition of the coefficient matrix? And our system is given here. Let's just take a quick look at what this system looks like. In equation form, this system in equation form is x1 plus 2x2 plus 3x3 equals 4. x1 plus 2x2 plus 3x3 equals 3. These have the same left-hand side, different right-hand sides. This is obviously an inconsistent system. The third line gives us 3x1 plus 2x2 plus x1 equals 2, 3x1 plus 2x2 plus x3 equals 1. Another inconsistency. We actually have two inconsistencies in this system. Our matrix is rank 2. How can we solve this system? Rank 2 matrix means that the columns also must not be linearly independent. Actually, we can see that if we add together the first row and the first column and the third column, we get 4, 4, 4, 4, which is exactly twice the middle column. These columns are not linearly independent. This means that we can't use the form of the pseudo-inverse that we discussed during our unit on projections in Unit 8, because our form for the pseudo-inverse that we used in that case was reliant of us on having a full column rank matrix. This is a matrix that is neither full row rank nor full column rank. Rank of A is 2, which is less than 3, which is of course less than 4. All right. So how do we tackle this problem? We use the singular value decomposition. Again, I'm giving the singular value decomposition here rather than working through it. Singular value decompositions are conceptually straightforward to evaluate. They usually end up being a bit of a pain to work with by hand. This is largely because we're forced to use orthonormal columns. For the singular value decomposition to work, we have to use orthonormal columns. This tends to lead to many radicals in our solutions, as we see here. Our U has fractions, sum of whole numbers and sum of radicals. Our V has fractions of radicals, and even our sigma has radicals in it. Right? That said, given the singular value decomposition, can we work with it in this problem? I recommend that you pause your video, try to solve this directly, and then continue. Okay. These sorts of problems, we take a two-step approach. First, we find a solution, a particular solution. We can find that particular solution, in fact, the particular solution from the row space, using a pseudo-inverse, but a pseudo-inverse defined with the singular value decomposition. Defining A plus as V sigma plus U transpose, we can use this pseudo-inverse, multiply it by B, and this will give us the best, in a least squares sense, solution to this inconsistent system, where that solution comes from the row space of A. Okay. What does this actually give us? Right, first step, evaluate A plus, given our A sigma V. Let's go ahead and calculate that pseudo-inverse. the pseudo-inverse Z sigma plus U transpose. V is found just by transposing V. So we're going to get rows of 1 over root third negative, a row with these root 2's, and a row with these root 6's, as we see here for V. Apologies. I was given this as V. We were not given it as V transpose, so we do not need to transpose this. V will stay as it is here, but we will have to transpose U. So our column of halves will become a row of halves. Same here, and these last two columns will become the rows of U transpose. This is what we see here. V U transpose, where the columns have become rows and vice versa. And what we need to put in here is sigma plus. Sigma plus is the matrix that we get by taking sigma. Sigma was 4 root 3, 2 root 2, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. A 4 by 3 matrix. And what we do is we take 1 over the entries of sigma where we have non-zero entries. So we take 1 over 4 thirds, 1 over 2 root 2. This 0 here we leave as a 0, and we change the size of the matrix so it becomes a 3 by 4, that it matches the flipped sign. It essentially matches the size of A transpose rather than the size of A. Constructing these matrices is fairly trivial given U, sigma, and V. Then we do the multiplication. I'm going to do the multiplication here in a slightly different order than I did one of the previous examples. I'm going to multiply the first two matrices for one reason. I have radicals in here and I'd like to get rid of them. When we multiply a V sigma plus with a diagonal matrix on the right, the effect of this product is to scale the columns of the matrix here by the diagonal entries of sigma plus. So this V sigma plus will have these columns scaled by the appropriate entries here. Negative 1 over root 3 times 1 over 4 root 3 is negative 4 times 3, or negative 12. So we get this, and we get this for every one of these because they're all identical. For the second column, we scale 1 over root 2 by 1 over 2 root 2. That's 1 over 2 times 2, or 1 over 4. So we get negative 1 over 4, 0, 1 over 4. Okay. The remaining pieces are zeros from these last pieces here, zeros and zeros. Note that this product has to be, this was a 3 by 3 multiplied by a 3 by 4. It has to be, again, a 3 by 4, which it is. We then multiply this by the 4 by 4 U transpose. And when we do this, we are going to be walking along each row of this multiplied by each column. We see that there's zeros and zeros that are going to be irrelevant. The only thing that's going to matter are these non-zero pieces. Negative 1 over 2 times negative 12 is 1 over 24. Both are negatives, so it becomes a plus 1 over 24 minus 1/8. Negative 1/8 is negative 3 over 24. Negative 3 over 24 plus 1 over 24 is negative 2 over 24, or negative 12. The second column, we have the same column here, so it's going to look exactly the same. The third column, we have a negative and a negative, so this is going to give us plus 1 over 24 plus 1/8, which is going to give us 4 over 24, or 1 over 6. Again, these two columns are identical, so these two columns end up being identical. For the second row, we actually only have one non-zero entry, so this is just negative 1/12 multiplied by negative a half, negative a half, negative a half, negative a half, a row of all 1 over 24. In the last row, the sign is changed in the second entry, so we have negative 1/12 times negative a half is plus 1/24, plus 1/8 is 1/6, just as we saw here, and plus 1 over 24 minus 1/8 is the same thing we saw before, negative 1/12. So we have our pseudo-inverse A plus written here. Once we have that, we can plug that in to find our least squares solution from the row space, multiplying this matrix by B, 4, 3, 2, 1. This gives us negative 12 times 4, negative 12 times 3. That's negative 7/12, plus 2/6, plus 1/6, so 3/6, which is 6/12. Negative 7 over 12 plus 6 over 12 is negative 1/12. For the second row, these are all 1/24. So 4 plus 3 plus 2 plus 1 is 10. 10 over 24, or 5 over 12. And for the last row, we have 4/6 plus 3/6, 7/6, minus 2/12 minus 1/12. So 7/6 minus 3/12 is 14 minus 3/12, or 11 over 12. This is our least squares solution from the row space. We can quickly plug this in and ask, what does AXR equal? Well, we have negative 1/12 plus 10/12 plus 33/12. That would give us 42 over 12, which is a little bit less than 4 and a little bit more than 3, as you would expect. It's in fact halfway between 4 and 3. This is 3.5. For the second row, well, we have the same row, the same row and the same piece, so we get 3/2 again. For the next piece, we have negative 3/12 plus 10/12 plus 11/12. So that would be 21 minus 3, 18 over 12, which is 1/2. 1/2. Right? 3/2 is halfway between 3 and 4. 1/2 is halfway between 2 and 1. This makes sense as a best approximate solution. We find an answer perfectly in between the two inconsistent pairs. Right? This is in the, and this happens to be in the row space of this matrix, and that can be shown also. Okay, we have a least squares solution, but this was not a full column rank system, meaning that we have many solutions, many equivalent least squares solutions. We can find a general least squares solution by adding in the null space. In this case, the null space has dimension 1, so what do we do for our general form? Our general solution is that answer we just got, the best least squares solution from the row space, plus any possible scalar multiple of a null space vector, AXN equals 0. These will all give us an equally good solution. They will all give us the same solution of 3 halves, 3 halves, 1 half, 1 half. So how do we get this null space? Well, the null space is already sitting in our answer. Remember that sigma was 4 root 2, 4 root 3, 2 root 2, 0. Oh, sorry, that should just be a, yep, okay. And 0, 0, 0. We had 2 non-zero singular values and a 0 here. The first 2 columns of V describe the row space of the matrix. The last column describes the null space. This already is a basis for the null space. It is sitting right in our decomposition. What does that mean? It means that we can just construct our general solution using the solution we found with the pseudo-inverse, and then adding in the null space piece. Our general least squares solution is our row space least squares solution plus any possible scalar multiple of a null space. Right. I hope that's given a flavor for how we can use the singular value decomposition to solve systems. The reality is that finding the singular value decomposition is something that is not easy to do by hand for most matrices. We typically use computational systems to find the singular value decomposition. But once we have the singular value decomposition, there are many things that we can do with it. Find low-rank approximations, perform principal component analysis, use the pseudo-inverse to find solutions to less than full-rank systems. That wraps up our videos for Unit 11, which also wraps up all of the videos for the course. It's been a pleasure teaching you. And if you have any questions, please don't hesitate to contact me. Thank you, and goodbye.